Greetings, everyone. Today we are going to talk about the heating curve of water. It's kind of a misnomer because, yes, we are talking about water, but it is not necessarily a curve. It's more of a zigzagged line. So, on the left-hand side of our chart here, we have temperature at at Celsius. So therefore, we know that 0 and 100 are important numbers because water freezes or melts at 0 degrees Celsius, and it either condenses or boils at 100. So as you can see, um, we have a line here in which we are graphing temperature on the vertical axis, and on the x-axis we have heat. So as we go from left to right, heat is being added to that of water. So on the left-hand side, we have this diagonal line. So as we start creeping up here, what this diagonal line actually represents is that of ice or solid water. But then when we get to a point at 0 degrees Celsius, we have a plateau effect. And this plateau is called this phase change. Okay, so it needs additional energy to make it over the hump or through this plateau, and we call this little transition period melting or freezing, depending on which way you go. So as we go from left to right, since heat is being added to this solid water, it is melting. But if we went from right to left, it would be freezing. So as you can see, the pictures above, we have solid molecules of water. Then we have this intermediate phase, this little slushy stage. And then finally, once we break past 0 degrees, then we are now in the liquid phase. And this is when the temperature actually starts increasing again until we get to 100 degrees. Now, we make it to our next transition phase. We have this gas liquid phase. So if we're going from left to right, remember the diagonals, the diagonal in which we were at 0 to 100, that's the liquid phase. Now we're at this intermediate phase. So we are now boiling or vaporizing. So heat is being added to the system. Now, in a second, I'm going to switch to my iPad and actually represent this picture to scale, because you need a whole heck of a lot more heat than what this picture is actually representing, because it's approximately a 40-to-6 ratio. Now, depending on where you're going, if you're going from right to left, you would be condensating. So heat would be released, and it would be going from the gas to the liquid phase. And then lastly, once we are at 100 degrees or higher, that is when you are in the gas phase. Now, whenever you're cooking, for example, it's really important to understand that gas has a higher temperature than liquid water. So the steam can burn you more so than that of hot water, because remember, liquid water can only at 1 atmosphere can only be between the temperatures of 0 and 100. Steam can go on a lot higher than even what's on this graph. So again, steam can be very, very, very can cause a lot of damage and be very, very traumatic. So and dangerous. Sorry, that's the word I'm trying to think of. Dangerous. It can be very dangerous. Yes, you can get hurt by liquid water, but steam obviously is going to have a higher temperature. All right, so on my iPad, I drew the heat curve of water at 1 atmosphere, and a little bit more to scale, because the transition periods at 0 degrees and 100 degrees have to be clearly written. So on the left-hand side, we have temperature. On the on the x-axis, we have heat, as heat is being added. Remember, heat and temperature are two different things. Whenever you see a diagonal, that is actually what you're normally used to as the state of matter. So each diagonal represents the state of matter, and so each diagonal represents the state of matter, and each horizontal is the transition phase. So we have solids, we have liquids, and then we have gas, okay? So what else can we write on here? Well, let's talk about specific heat capacity, because that's what we've been discussing this unit. So the specific heat capacity is going to be different based upon whether you have solid, liquid, or a gas. So up until now, the specific heat capacity has always been, for liquid, the specific heat capacity should be 4.184. And remember, it's joules for grams degrees Celsius. All right, so we've used 4.184. But water has a different heat capacity if it's at a gas or a solid. So when it's at a solid, its specific heat capacity is actually 2.1 joules per gram times degrees Celsius. And then when it's at a gas phase, it's actually 1.99. So gas and solid, or gas and water vapor and ice, or gas and solid, really are very, very similar in terms of their heat capacity. Just know that liquid water is has the highest. I'm going to put my units down, joules for every gram, degrees Celsius. Okay, what else can we talk about that pertains to our heat chapter? Well, whenever we are on these transition phases, we have specific heat capacities. Therefore, we are going to use MCAT. We can use the formula for Q equals MCAT on all of these transition phases. So we're going to be using Q equals MCAT there. We're going to be using Q equals MCAT here. And then we're going to be using Q equals MCAT whenever we're solving for problems on the diagonal, or when we're discussing solid, liquid, and gas. We're going to be using the formula for MCAT because we have a specific heat capacity that's different for each one of those. All right, so let's start talking about these transition phases. So we know that we're going through a transition phase at 0 degrees Celsius. It's kind of slushy. Depending upon if it's going from left to right, it's absorbing heat. If it's going from right to left, it's releasing heat. So when we talk about this 0 degrees phase, when we go from left to right, we're going to call that the delta H of fusion. And the delta H of fusion actually has a specific amount of heat required to go from point A to point B. That is going to be a positive 6.01 kilojoules. It takes, for 1 mole of water, which is the same thing as 18 grams, in order to go from point A to point B, it's gonna take an additional amount of energy. Okay, so it's 6.01 kilojoules. Conversely, if we were to go the opposite direction, and we were going to go right to left, we actually has a different term, and it's forming a solid. So therefore, it is delta H of solidification. And since we are not absorbing heat, we are releasing heat. Therefore, we are going to be negative 6.01 kJ, kilojoules. Don't forget that negative symbol. Actually, you know what? Let me clean that up just a little bit. All right, so it's going to be negative 6.01 kilojoules. Now let's talk about the phase change at 100 degrees. Well, now that we have a little bit more room here, because as you can see, it's going to take a lot more heat for the same amount of water. It's going to take a lot more heat to boil it than it does to melt it, and you'll see in just a second. So if we are going from left to right, we're going to call that the delta H of vaporization. We're creating a vapor. And as you can see, this horizontal line is a lot bigger stretch than at the 0 degrees because of the fact that it takes more energy to boil. So it's at 40.7 kilojoules of additional heat to make it past this transition phase. Conversely, if we were going in the opposite direction, we're going to be calling this the delta H of condensation. How much heat is released during this condensation phase? Well, instead of positive, it's going to be negative. Negative 40.7 kilojoules. So as a quick once over, when you are at the diagonals, you're at solid, liquid, gas. When you're at the horizontals, that's the phase change, and it needs additional heat. And we're going to use these numbers in the next lesson. 6.01 is at the 0 degrees. It should be positive or negative depending on what direction you're going. And then at the 100 degrees, which is the next phase change for water, it's going to be 40.7, positive or negative depending upon the direction. And last thing to discuss is kinetic energy versus potential energy. If we go from, every time we are going on a diagonal and we're going up and the temperature is changing, keep in mind that the temperature is changing. The kinetic energy is proportional to the temperature. Okay, and then when we are on the horizontal, although the temperature may not be changing, nor the kinetic energy, but we are still adding heat. Heat is still being required, so we are gaining potential energy. So potential energy is those phase changes. Kinetic energy is at solid, liquid, or gas when the temperature is actually changing.